Let us now look at two different random walks, basically on a graph that is very linear in structure. But we'll see that the two random walks have very different characteristics, in particular, very different stationary distributions. So here's one. We have vertices, arranged in a linear order, starting from 0 to n. And here are the transitions. With transition probability half, you move forward, and with probability half, you move backwards, except for the two very last vertices, the 0th vertex and the nth vertex, where there's no way to. So, for example, in the 0th vertex, there's no way to go backwards. So we have instead a self loop with probability transition probability half. So now this is one random walk, and let's also look at a second random walk that has similar structure. Again, you have vertices from 0 to n, and similar to the previous one, you have forward transition probabilities half, and in this case, instead of just stepping back one step, we transition all the way back to 0 with probability half. So the first random walk can be thought of as a sort of an undirected random walk, but this one is the direction is exploited, so you actually return back all the way to 0. So these are two stationary distributions. Let's try to understand, what is, so these are two Markov chains or random walks rather, and we'll try to understand what their stationary distributions are. In this case, here, what do we notice about this graph? Well, this random walk. Well, if you look at, um, let's try to work out the transition matrix. Now, the transition matrix, let us look at the node I. Okay, the node I can move with probability half. So this will be, let's say, I minus 1, I, and I plus 1. If you notice, the probability of staying in I itself is a 0. But if you look at the probability of transitioning to I plus 1, that's a half. And moving backwards to I minus 1 will again be a half. Okay, so the probabilities in any row will add up to 1. So clearly this is a stochastic matrix. What about the columns? Well, if you look at the to fill in the columns, we'll have to know how the probabilities are coming into vertex I. So from I plus 1, you can move to I with probability half. So that will be actually a half over here. So it's I plus 1 here. And from I minus 1, you can also move in with the probability half. So again, if you look at the columns, the probabilities add up to a half. So what we have here is a doubly stochastic matrix, which immediately should tell you that the stationary distribution is the uniform distribution. How about this random walk? Now here, if you think about it, there's a much higher probability of staying in this being in this vertex. In fact, wherever you are, with probability half, you'll be coming to that vertex. So that immediately tells you. So now we're speaking more intuitively, and you should verify this more carefully. it immediately tells you that the stationary distribution entry corresponding to this particular the zeroth vertex is going to be a half. Okay, um, and then so what's the probability with which a random walk will be in this vertex? If you think about it, the only way you can get to that vertex is by um, being at vertex 0 and then making a transition into this vertex. So you'll be in vertex 0 on with probability half, and we've kind of made an intuitive statement towards that effect already, which means that you'll be so you'll be in this vertex 1 uh, with probability half times a half. So that's going to be a fourth. And then here you'll be here with probability similarly an eighth and so on. And here's and it's you should now um, verify that this is in fact the stationary distribution for this Markov chain. So now for that you have to actually write out the transition matrix, multiply it with pi, and ensure that it actually gives you pi again. So that's something that is left for you to verify.